Hi everyone, and thanks for attending this talk. My name is Emmanuel Dufour from the African Institute for Mathematical Sciences and Stellenbosch University, and this work was done together with Bruce Bassett and it's titled Deep Evolution for Facial Emotion Recognition, and thanks to the NRF and AIM South Africa for funding this research. All right, so I'll start off with an introduction to facial expression recognition and then talk about the research objectives on reducing neural network parameters and increasing transparency and explainability for emotion recognition. I'll introduce the proposed algorithm and then we'll talk about the results and the experiments conducted. So what is facial expression recognition? Well, humans convey their emotions across in various forms, one of which is expressed through changes in a person's face as a consequence of their emotional state. Facial expression recognition is the ability to recognize the expressions that are being conveyed through these changes in the face. Paul Ekman defined six basic classes, which are happy, sad, surprise, disgust, fear, anger, and the seventh class just being the neutral class. So what is automatic facial emotion recognition? Well, let's say we have a system for which we can input some images into some algorithm, and the output of the algorithm is the emotion that's being expressed. So, for example, angry, disappointed, or surprised. Here's an example of inputting an image into Microsoft's Emotion API. And you can actually go to the website and try it out for yourself. You can upload an image and it will return a JSON output containing the scores for the various possible emotions. Well, why do we care about automatic facial expression recognition? Well, here's an example from a study, and I'll just read part of the abstract, which says, for example, a social robot would be able to encourage a cancer patient to take their medication in a more efficient manner if it could understand the emotional state of a patient. So what is the state of the art in terms of methods to tackle emotion recognition? And the current state of the art is to use a convolutional neural network. So let's have a quick recap as to what is a convolutional neural network. Well, typically we'll input some image, for example, and then we'll have some convolutional layers that have some nonlinear activation function. So for example, the ReLU activation function. And then we can make use of max pooling layers, which reduces the feature space. And then we can have more convolutions and max poolings. And then eventually we flatten everything out. And then we can have fully connected layers. And finally, the output layer, which tells us, which typically uses a softmax activation function to assign a probability depending on the class of the input. So deep CNNs, or deep convolutional neural networks, typically results in better performance than more shallow CNNs, but the deep CNNs also have a lot of trainable parameters. And these very large CNNs tend to have very long training times, especially on limited hardware. And in terms of inference, are actually problematic for running on devices that have very limited hardware, so for example, edge devices. So our research question is, can we optimize the performance of CNNs for emotion recognition and reduce the number of parameters, so the number of trainable parameters, and improve the explainability? So this refers to the theme of explainable AI, where we not just building models that we can't understand, like black boxes in the deep learning era. We want to build models that we can try and help humans understand what is going on and why the model is making certain predictions. And of course, the final goal is, so we want to reduce the parameters, improve explainability, and also without compromising on the classification accuracy. So we propose to use evolutionary algorithms and neural network frameworks to create the deep evolution for facial emotion recognition, DEFA. And the proposed algorithm was built using Python and TensorFlow and Keras. So here's a typical approach where one would have an input image and we would maybe do some pre-processing and then put it into a CNN, train the CNN model, and we would get a classification output. But in our case, the input is not the complete image, it's extracted patches. So we extract certain patches, we input that into the CNN, train the CNN, and then get a classification output. So in a typical approach, we would have an input image, which we would convert to grayscale. Here, for example, 281 by 381 by 1, because it's a grayscale image, which is a total of roughly 100,000 pixel inputs. In the case of the proposed algorithm, here are 4 patches that have been extracted from the image, each of which is a 50 by 50 pixel size patch, resulting in a total of 10,000 pixel input. So how do we find these useful patches? And are the ones on the left good patches for emotion recognition and for training a neural network? And the patches that are shown are actually not very helpful. Just looking at that part of the eye doesn't actually help us understand the emotions that are being conveyed. So how do we go ahead and find these useful patches? So we propose to use evolutionary algorithms. And here is the basic outline of the evolutionary algorithm, and then I'll talk about the proposed algorithm in the context of the evolutionary algorithm. So the first step is to initialize a population of chromosomes, and in our case, a chromosome looks something like this. We have an alpha parameter, which dictates the width of the patch, a beta parameter, which dictates the height of the patch, and the x and y coordinates of the top left corner of the patch. So here you can see on the right that the x and y coordinates are relative to the nose. So the first thing to do is to find the location of the nose, and we use dlib and OpenCV to do that. Then from there, we can translate and move to position x and y relative to the nose, and then use alpha and beta to get the patch. Now here is an example where we have 2 genes. So the number of genes determines the number of patches to extract. So here we have 2 genes, so we would extract patch 1. So we can see an example of patch 1 being extracted relative to the nose, and patch 2 being extracted also with coordinates x and y relative to the nose, and the size of the patch is determined by the parameters alpha and beta, which are also encoded into the chromosome. And the values for x, y, alpha, and beta, when we initialize the chromosomes, are randomly generated in the initial population. And we can add some constraints to the values of alpha and beta, or we can let them be completely random. And we impose a rule that there is at least one patch within the gene, and the user can define the maximum and set an upper bound to the maximum number of patches. And initially, in the initial population, the chromosomes extract bad patches. So here's an example of 2 patches that were extracted near the eye, and these are not very useful for emotion recognition. And the patches are stacked on top of each other, like an RGB image has 3 color channels. So there's a red, green, and blue channel stacked on top of each other. The patches extracted by the proposed technique are also stacked on top of each other. Okay, so now there are a few other steps, which we'll come back to, but let's jump to the genetic operators part of the algorithm. So here's an example of crossover where we've selected 2 parent genes, and both parent genes have 2 genes, so 2 patches, and they have different values of alpha and beta. So the first step is to just randomly decide on which gene to modify, and then we just swap them around and we create 2 offspring. So in this case, we've taken the first gene from parent 1 and put it into the place of the first gene of parent 2, and the first gene from parent 1 and put it in the first gene of the first offspring. So here I refer to genes, but in this case, the word gene means patches. And we propose 3 different types of mutations. So we can add a gene or add a patch, we can remove a patch, and we can shift that patch. So shifting we get the x and y coordinates of the patch, and then we perturb it by some small delta parameter. So we would get a new x2 and a new y2, where we simply take x1 and we add some small delta to that, and then y1 and we add some small delta to that. So we're able to get new values and shift the patches around the image. And the user can constrain the size of the value of delta within a range if they want to. So here's another example where we've made a different shift on the image on the right. So this is a much larger shift. So the shifts can be small, depend if we make the values of delta small, or larger if the values are larger. And we can also just tell it to randomly select between a lower and upper bound. So next, let's talk about evaluating the population, or evaluating a chromosome. So to evaluate a chromosome, we have to go back to the original research question, which is about optimizing the performance of CNNs and reducing the number of parameters without compromising on the classification accuracy. So to do that, we need to first get a baseline metric. So we have our data set for which we would do all sorts of pre-processing, and we would try and optimize the best CNN to that data set, and we'll train it on that data set, and then evaluate the performance on some validation data. And that essentially gives us some baseline metrics in terms of the validation accuracy and the number of trainable parameters in that network. Now that we have those baseline metrics, we can now evaluate the chromosome. So we take one chromosome and apply it to each image in the training data set. And essentially, a chromosome extracts patches. So depending on the number of patches in the chromosome, we would extract 1, 2, 3, or 4 or more patches. And by extracting the patches from each image, it helps us essentially create a new stacked data set. So I say stacked because if there are 2 patches from each image, then each new image has 2 channels in it. And the new patch dataset is now input into the same CNN for which we train and compute the validation accuracy as well as the number of parameters in the model. So now we can come to the fitness evaluation, or the chromosome evaluation, and here is the calculation that we propose. We assign some weight to the value of V, which is the validation accuracy divided by the baseline accuracy. So this is validation accuracy on the patch and validation accuracy on the baseline. And then the term P is the number of parameters in the baseline minus the number of parameters in the chromosome divided by the number of parameters in the baseline. And we assign a weight WS to control the effect on the importance of the validation. So each chromosome creates a new patch data set, and the same CNN that was used as a baseline metric is used in this case on the new data set. And we calculate the metrics for each of the chromosomes. So there's a lot of computation happening. Here are the data sets that we used to evaluate this approach. There was the Jaffe, KDEF, MUG, and RAFD datasets. And each of these datasets have various characteristics based on the ethnic diversity, the age groups of the participants, and different lighting conditions as well. So how do we validate our approach? Well, the fairest approach to validating in terms of testing generalization ability is to ensure that a subject is only used in training and not in training and testing. So if a subject is present in training, then the same subject should not be present in testing. So this is the most fair approach. And so we took that approach, and we also had a 70-30 split between the number of images in training and testing. And then we repeated everything 10 times and averaged our results. And we did some image pre-processing, such as histogram equalization and converting to grayscale, and also image augmentation to increase the number of examples in the datasets. Some of the datasets had very little examples. So we did things such as horizontal flipping, blurring, add some noise, and random rotation shifts between -10 and 10 degrees. And this was implemented using IMG.org. So let's have a look at the evaluation performance. And so here I present the baseline accuracy of the model. So this is the case where the images were input directly into the CNN, for which we optimize the network and then train it on the original images. And then the second column contains the proposed approach where we extract patches from the image. So we don't train on the original images, but we train on the extract patches, and I also show the difference. So in some datasets there's a small difference in performance, and in some datasets there's a large difference in performance. And to determine the CNN, we studied a lot of articles and literature, which helped us guide our decisions in building the CNN. And here's also a table that shows a difference in parameters, since that was one of the things we were interested in terms of our research objectives, was to reduce the number of parameters without having a big loss in performance. Or in some cases, as shown on the previous slide, we actually had an improvement in performance. So here we can see that in some cases, we've reduced the number of parameters from 1 million to 2 million to 7 million parameters, representing a reduction from 88% to 98.2% on some datasets. And these refer to the number of trainable neural network parameters. So here are some examples of the patches that were extracted from generation 0 and the best chromosome from generation 15. So here we can see in generation 0, the best chromosome extracted 2 patches around the eye, and in generation 15, the best chromosome extracted 2 patches as well, the first being around the eye and the second being around the mouth. Here's another example. In generation 0, the best chromosome had 4 patches and extracted patches around the clothes and the neck, the top of the eye, and the ear. And in generation 15, the best chromosome extracted a patch that contained the mouth and kind of the eyes, the nose, and the mouth. To conclude, evolutionary algorithms can still play an important role in the deep learning era. And combining the evolutionary algorithms with deep neural networks can lead to very interesting results and new research avenues. And reducing trainable parameters, in other words, network compression, is important, especially in Africa, where access to GPUs and hardware for training is more challenging as opposed to other places. So building models that can run on limited hardware is important. And the proposed technique led to better generalization, and the resulting model is actually quite explainable and transparent. We can see the areas that the proposed technique is focusing on, and we can better understand our model as a whole, making steps towards explainable AI as opposed to just using everything as a black box and not really understanding what our model is doing. And in terms of real-world applications of this, in terms of small compute, touching back to the point of model compression, well, you can think of having this technique in small devices such as Raspberry Pis and monitoring things such as pain detection. So there's a study that emphasized the use of motion recognition in understanding pain when the patients, for example, could not express pain. So the study suggests that people tend to express pain verbally, but what if you're unable to speak? Then another way to understand pain is to look at one's facial features and facial emotions. So these are just some ideas where we can use these models in small devices and that have very limited hardware to try and make some kind of an impact. So thank you for attending this talk, and please feel free to ask questions and reach out via email as well. Thank you.